Ah, then they cannot connect to the class. Mm. Okay, one person. I don't know why they're connecting. Hello, can you hear me?
Hello, good evening.
Hi, good evening. All right. So one person that could hear me
Hello,
clearly.
good evening.
Hello, I can hear you. Can you hear me?
Okay, I can hear you.
All right, that's much better now. There are still others trying to join. So if you guys can actually hear me, just unmute your listener and say something so I know that everyone is hearing me. Okay. All right. That's good. So without further ado, let me just quickly start by sharing my screen and not waste much time. So yeah. So the what we hope to do today is the data modeling, machine learning for classification taxes. I will quickly take a review of all right. You guys can see my screen. That's good. I'll quickly take a review of our previous class on regression, where we talked about what data modeling is all about. That's yeah, we talked about data modeling being the process of creating a machine learning model capable of predicting label from futures, tuning them for business needs, validating it on other data, and like that. Just trying to explain what the bulk of data modeling implies when we talk about this aspect of machine learning. And we also talked about why we model data. We talked about the various steps in modeling data, where we created this checklist. That's preparing the data, future selection, future engineering, future scaling, and then shortlisting promising model, fine-tuning the model, and all of those stuff. So what we'll be doing in this class now is we'll be jumping straight into the classification data sets. And the data set we'll be making use of is the loan prediction data set, which is the task that we'll be doing for the classification now. And just to give you guys an overview of the data sets, this is the data set. We have a series of columns here. There's the loan ID, there's the gender. That's okay. Let me increase my just to ensure that everyone can see it. Maybe too big, but it's still okay. Yeah, so there's the loan ID, there's the that is the ID of the loaners, those that actually made the loan. There's the gender, then there's the marital status, whether the person is married or not married, indicated by yes and no. Then there's the dependents, that is how many people are actually dependent on this person that is actually requesting for a loan. There's the education, whether a graduate or not a graduate. There's the self-employed, if the person is self-employed or not, maybe the caller worker. Then there's the applicant's income. That's the amount the person receives. Although it wasn't really specified for us what the applicant's income should be. That's if we talk about the feature column description. Now that just says that the applicant's income. So we don't know the value, whether it's in dollars or something else, but we'll just assume that it's in dollars. Yeah, assuming the applicant actually has a co-applicant, this is the future column for the co-applicant. And those that don't have co-applicants, I think they are represented by the value 0. So we know that this particular applicant has no co-applicant, so the value here is 0, and the same for every applicant without a co-applicant. Then there's the loan amount. That's the amount that they intend to loan. The loan amount 10. And I really don't understand what this future column represents, but over time we'll get to know it better. Then there's the credit history. The credit history, which has a brand of information of its own. There's the property area. That's the area where the applicant has a property located in. Is either it's a rural area, a semi-urban area, or an urban area. Then there's the loan status. That is whether the loan is approved or not. So this is just like an overview of the data sets. Okay, I'm glad to say that a lot of people are already joined in. So this is the overview of the data set. So we'll just jump right in to processing the data sets, and I hope you guys have had time to like go through this notebook. If you realize, it's kind of similar. That's when you start with the notebook. You realize that it's similar to the previous notebook on the regression task. But when you get to directly from this stage, you see that there's a lot of changes. The futures are different. The processes that need to be followed are different, and all of the, there's just a lot of changes, and that's because the two data sets are not the same. And the most important change I want us to note here is this particular change here, where we talk about the loan status, where that's the results here now are categorical. That is, it's either yes or no. And I want to just use that to quickly talk about what a classification is. We talked about regression at a point being the ability to model a line through the data points. All right. So we say when we want to create a model, a regression model, we want to find a line within the data that best fits the prediction points or the value points now that the model is guessing. But a classification problem is kind of different. When you classify, the term classification is straightforward. You're either trying to classify that it's either a value or another value. And there are two types of classification, if we have to be precise. Okay. There are two types of classification. There's a binary classification and there is a multi-class classification. What we have here, that's the problem that we have here, is what we call a binary classification. A binary classification is a form of classification that only produces two values. The term binary comes from 0 and 1. So it's either a 0 or a 1, a yes or a no, a true or a false, and just that kind of thing, a cat or a dog. So you're either trying to predict one value or the other. While a multi-class classification is more complex, but not entirely that complex. But what a multi-class classification is all about is when there are more than two. So basically, if you have any form of classification that has maybe yes, no, or maybe, it becomes a multi-class classification because it's no longer binary. It's not predicting either a value, one or the other. So with that out of the way, I would just jump straight into our practical notebook because I've already said I would love to maintain the integrity of our work notebook as much as possible. So we'll just go straight to this notebook. But before I do that, I like to copy this cell so it'll be easy for me to process everything here. So loading the, oh yeah, I haven't imported the necessary tools. So import NumPy as entry. So as loading the data set now into our file, we have the loan data set, which is the variable we use and we use to store the data frame, the loaded data frame into the data. And compared to what we did in the regression task, you realize that we actually set the index column here to the loan ID. The loan ID now represents the unique identity that each applicant has. And one thing we realize about the unique ID is that there's actually no correlation between these values. And you could do your check-ins now to confirm if there's any correlation, like as we did when we were talking about the regression tax in the, I think it's the item ID or something. It just has to do with the ID of the item. But yeah, the loan ID is quite unique. So we use it to represent the ID. So instead of it being 0, 1 and the likes, the loan ID will be representing this. And the first thing I want to do is I want to like prepare this data set because I don't want to like reiterate the process now of going through this list of preparing the data, preparing the data, shortlisting model, fine-tuning. No, I just want to prepare the data. Then we'll walk straight on some kind of very important stuff. So that is like skipping ahead. I just want us to skip ahead directly as soon as we can. So I created a function that will actually prepare the data frame, and the name is this prepare data set, and that will be loading the it would be loaded directly from the loan prediction file. So I'll just say from loan underscore prediction import. So that's it. We'll be importing the file into our the function rather into our system, into our notebook here, and we'll just quickly prepare the data frame. So say prepare. The name of the data set is the loan data set. So that will quickly prepare the data, and I'll just use this to preview the data that we claim to have prepared and see what's changed. Now realize that the gender has been encoded, so as the married, so as the dependent. Basically, all the future columns has been encoded right down to the loan status. And having that now, we can proceed to what I want us to really check. Now that is future selection, selection, making use of future importance. So this is what we just want to, maybe I should make this bigger slightly. So that's it. Okay, so this is what we are trying to do now. We want to select the futures that, or process the futures that we feel are going to be more necessary. Because if you look at the data set now, let's quickly just have an overview. The loan data set has a shape of it has a shape of 614 by 12. And what that means is that there's actually 614 rows. That there are 614 rows. So that's from here, the top here, all the way to the bottom. They actually have a count of 614 rows. And then there are 12 future columns. So the genders, so the gender, the married, the dependent, education, self-employed, all of these are the future columns. Now, it is true that all of these futures may play a part in the final goal, which we are trying to predict, which is the loan status. That's whether it's either yes or no, represented by 1 or 0. What we hope to attain now is to decide on which futures, that is, select which futures are more accurate for the model, so to say. And one of there are actually two machine learning models that are capable of doing this. There's the decision tree and there's the random forest. And the decision tree is actually the primary model that is capable of checking the importance of a future in a data set. Since the random forest is an assemble of decision tree, it also has the ability to do this. So we'll just create a dummy random forest classifier now. That's the random forest classifier. And try to check out how this is going to work. One of the first things we really need to do is we need to split our data sets. And by splitting the data set, we need to first start by classifying which data is which is the training, like the data, and which is the target. We already know that the target column is the loan status. So we'll start by working on the separating the loan status from the entire data set. Now, we do this by saying set the target column equals, so that is the target column is the loan status. Now we want to quickly get our target data. I will say the target data equals to the loan data set that target underscore column. That's for the target, and for the data, we just want to drop the I want to drop the target column now, but not actually making the drop in place. So whatever is returned should be stored in the data variable. So for the we set this to the target column. Then we'll say the axis equals 1 to indicate that we're actually working with the column. So this will give us our data and our target. And if we quickly preview our data, what we realize is that it's basically the same thing from what we had earlier, just that this time around there's no loan status as part of the listing. So we have our data sets properly set up. And now we have 614 rows. We need to split our data sets now into two, the training and the test set. And I believe you guys must have seen the, because I actually attached 2 other notebooks, like steps involving selecting large data sets and then the other steps involving selecting smaller data sets. When working with a smaller set, you try your best to avoid creating validation sets from smaller sets, because we don't want to reduce the size of the data, given that for smaller sets, the data, the amount of data points available are already small enough, and we want the model to be as accurate as possible. And one of the ways to create a model that actually understands that can actually find the a precise enough pattern now in the data is by having enough data to feed it with. Now, this particular amount of data that we have, 614, is already small enough as it would be. So if we were to split the data set, we want to split it to a kind of value that is kind of small. It's smaller actually, but the test set isn't going to like negate the effect of the whole data set, the training data set while we train. So we want to have something like, say, 500 data for training, then maybe 114 for testing. And one of the ways we could do this is by just do a quick math. If 614 is equals to 100%, 500 is equals X%, that is like saying 500 divided by 614, 614 as 10 points. Divided by 614. Okay. That's like saying this would be 500 represent about 80%. That's approximately 80% if we were to be rounding down. So if we wanted to, a good size for the test set would be, say, 2.2%. So we just import the train test split for splitting the data sets directly from our, we import the train test split for splitting data, the data from our scikit-learn model. So now we sklearn.model selection report. So that will import the necessary function now to split the data. And what we want to do when we come here is, as I said, I always like to look at the documentation when I'm trying to like split the data. And this is what I usually come to look for. Yeah. So I want to just copy this particular value, and I can't always remember the pattern in which is arranged. And that's because the pattern is, I think it's kind of different with that of TensorFlow. So if we do this now, if we say the test size, that the test size equals to 20% random state. I just like setting the random state. So we have a constant result whenever we run the notebook. So that will be test size, random state, SAS42. And I think, okay, the shuffle too could be set. We set the shuffle to true just to make the model more precise. There's something else we could do. There's such a parameter called stratify. And what this stratify does is that it stratifies the splitting in such a way that the balance between that is the equilibrium that exists between both classes. That is the final classification, which is either yes or no, remains the same. And what that means is that if the data set has 80% of yes data, that is, there are more yes category now. That is assuming one represents yes. There are more yes categories, or yeah, there are more yes categories compared to the no categories. Whenever I'm splitting the data, it tries to maintain this balance with between the yes categories and the no categories in such a way that in the training data, it doesn't the yes category does not overwhelm the no categories, and the inverse is the test data. But I will leave that up for you guys to just research and maybe test it out when you are working with the data set. But for now, though, I will just come here and make use of a simple thing, because what I really want to do is check the future importance of each future. So I'll just come here just for us to preview how did this thing look like. So for the training data, we have about 491 data points. And for the test data, we have 123 data points, which is is good enough actually for what we hope to achieve. So for me now, I'll just go straight to creating the model. We'll create the random forest classifiers by saying from citizen.symbol import the random forest classifier. So that is it, the random forest classifier. I like to quickly name it as RFC for random forest classifier. So we leave the default parameters the way it is. Yeah. And then once I do this, I would train the random forest classifier on the training set. I'll train it on the training set. So that will be okay. So that will be the RFC.fit. So we are fitting the model with the train and the test. Okay, we're having a value error. So, I feel the reason why we're having a value error is because there are a couple of columns here that are not properly that contains NaN value, that is, they contain empty value. I thought I've worked on all of this stuff, but let me just quickly check. So I'll say I'm not the head now, that's for the info. So okay, the married category is missing one particular value, and that's why it's giving us all of this error. What we'll do is we'll quickly amend that by saying the married, I think, dot forward field in place. We'll set that to 2. So what that will just do is for the married data set, with wherever the value is actually missing in the data set, it just perform a forward filling to fill that missing point, which is going to be just 1 from what we can see here, because every other thing points at 491, which is the exact same value we have for our training set. So just run this and run this again. Now our RCF model has been fit now. What we want to do now is we want to check for how the future importance of the model. And the way we do this is by saying this RCF dot future importance represented by this. Now, if you were to output this value now, what it shows is this. And what this is like the percentage from 0 actually means 0% importance, while 1 means 1% importance. And basically, within all the futures, it tries to calculate how important each particular future is to our data set. So this is the importance of the gender future, the importance of the married future, the importance of the dependent future. And this may be hard to see given the order in which it appears. So what will happen is we will try to print it out now. We'll just try to print everything out. We'll say we'll ask for the column and the importance in the columns and the what is the name now? These are the 2 things we want to look through. So we are looking through the column and we are looking through the importance. So if we say zip, just want to put this out in the zip, I want to print out these 2 things. So we'll be able to have a visual of what is actually happening when we're talking about the importance of a column. So say, so basically, this is what we're talking about when we talk about the importance of the column. It's saying this is how important the gender column is to the data set. This is how important the married column is to the data set, the dependence, education, and the like. Now, I believe that one point I actually talked about the importance of these various columns when I talk about the future selection, and I just wanted to highlight that case in our notebook here. So when talking about the importance of the future column, one of the things we looked at is we try to order it in this supposed to be within the future and their importance in the order of their importance. Now, this is the major thing I want to highlight here. So we want to look at which future column is more important than the other. So from what our random forest model was able to do, it was able to point out the most important future in the data set to the least important future in the data set. And we did that by printing out the results here. So we say that the most important future in the data set is actually the credit history, the applicant income, the loan amount, the co-applicant income, and all the way to this. So the least most important feature is whether the person is self-employed or not. It really doesn't, what that means is that it carries little weight in deciding whether the person will actually get a loan or not. Same thing with the gender, same thing with the education. So these are the least most important columns in the data set. And based on the requirements that you wish, now that this is assuming that you were not actually working on a practical system, because at the end, the goal of this tutorial is to prepare you guys for the so-called the hackathon, right? So the goal of knowing what future is important over the other is that you are better able to reduce the number of future columns to improve your data set. So from here now, you could decide that, okay, in this data set, you want to work with just these 3 columns. And quite all right, I won't recommend this because the more the future columns too, the better the model, will be. But you could decide that, okay, this particular set of futures are the most irrelevant. Maybe we should drop them. And if you make that decision, you could quickly drop these columns and work with the rest of the ones that you feel to be more important. And this is just a suggestion, actually. I think in our data set, what we tried to do was that we dropped the gender and the married column, because personally, I feel they are the 2 most irrelevant columns to decide whether an applicant, gets a loan or not. So that's a quick overview of what how to select a quick overview of using models to select futures when working with the data set. So aside from, okay, this is where we drop the gender and the married futures. Aside from that, one other thing I really hope we could, one other thing that we need to talk about rather is the final stages. We need to talk about the various classification metrics now. When we talked about the regression metrics, we talked about the MAE and the MSE, and we talked about how they work. But now, when it comes to classification, the metrics that are being used are kind of different. And the way we start talking about this is by talking about the confusion matrix. Now, what is the confusion matrix? Basically, if you want to think of a confusion matrix, this is just think of this short box. Now, this short box is a quick overview of what a confusion matrix aims to achieve. And what it does is that when it makes prediction on a data, it takes it divides the prediction into 4 sets. Now, the upper bound here represents the actual values. Now, what the actual values means is that, okay, what the data set actually says about this value. And maybe I should quickly write out what I'm talking about here. So I would, because we have our test sets now, I will quickly predict our test sets, saying the predictions equals RFC, which is the model that predicts. But what are we predicting? We want to predict the X test. So that's for the prediction. And probably, I'm guessing we have the same issues. I really think I thought I've fixed all of this. So see, X underscore test dot info. How many values are missing in this one? 1, 2, 3, 1, 2, 3. And it happens to be the same thing with all our issues coming from the married column now. So we just apply the same fix that we did when we were talking about the training set, which is this. We'll apply that fix here. So just say Ctrl. So okay. So that's it. We say predictions equals that's the RFC, the name of the model that predicts. Let's predict. And what are we predicting? Now that's the X test. Now the predictions. Now that we've made the predictions, we want to import the confusion matrix now. Import from dot so this is the how you import the confusion matrix. All of them, every form of matrix for validating how a model performs is always stored in this model named matrix. So we just say from scikit-learn.metrics import confusion matrix. And when we say the confusion matrix, just as we did with the MAE and the MAE and the MSE, you first enter the actual value, which is the y test, and the predicted value, which is the prediction. Okay, not prediction, but predictions. What this generates is the matrix here, now representing what we're about to talk about at this point. So the upper bound here represents the actual prediction. That is what the model actually predicted. And the lower bound here represents the model prediction. Now, this is the actual prediction. This is the model prediction. And you know, we are comparing both the actual and the model prediction to each other, right? So the true positive here represents the scenario where the model predicted positive and the actual value is positive. What this means is that, okay, a situation where the model was actually the model predicted that, okay, the value is actually a true, a yes now, and the actual value as indicated by our data sets at any point now is yes. At that point, it adds to the true positive. The true positive just represents that, okay, the model prediction and the actual prediction agrees. And it's the same here with the true negative. When they both agree that the value is negative, that is not 1, and they both agree that the value is 1. So this green diagonal here represents where they both agree on the positive result and on the negative result. So if the actual value is actually true, and the predicted value is true, it's what represents a true positive. But if the actual value is false and the predicted value is false, we call this concept the true negative. The inverse is the same here, where the actual value is actually a false, but the value is predicted as true. This is the concept of false positive. So basically what this means is that the model is predicting a positive value that isn't positive. All right. So the model is predicting that a value is positive, whereas it is negative. And in this scenario, the model is predicting that a value is negative, whereas it is positive. It's just like asking a machine learning model to predict if a lady is pregnant now, and the model is actually predicting that she's pregnant, whereas she isn't. Now that's a true false. That's a false positive rather, because the outcome is that she is pregnant, whereas she isn't. So I have a question saying, can I explain the future selection again? All right. The thing is, this video is about to come to an end. So maybe in the next video, I would start by explaining the future selection once more. All right. So just for the sake of this video, I'll just quickly complete what I was saying here. So we're talking about the true positive, the true negative. So where the model and the actual value and the predicted value agrees to either be positive or negative. And the inverse is the same for the false negative. Now, every other metrics, that's the accuracy, the precision, the recall, the F1 score, are all deduced from this confusion matrix. And how this works is there are a series of formulas that are kind of highlighted when we come down here. I think, yeah, when we come down here. And I would take a little while to explain each and every one of these formula, at least so that everyone can understand. So since the video will be coming to an end anytime from now. I hope you guys are preparing for the next session of the class. And what we'll be doing is we'll first start by explaining again what this future selection is all about. Then we'll talk about the accuracy, the precision, and the recall and the formula, and how these formulas affect the metrics that we are going to be making use of. So I hope to see you guys soon, at least in less than a minute's time or so. All right.